Hello Year 11s and welcome back to Mathematics. In today's lesson we're continuing with our section on surd laws, and what we're going to be looking at is a thing called rationalizing the denominator. So last lesson we looked at our arithmetic with surds, and what we did in particular was simplifying with surds. So we tried to find a perfect square, the greatest perfect square factor. Then we also did addition and subtraction with surds and also multiplication. Here we're kind of dealing with division with surds, through a process called rationalizing the denominator. So if you have a look, this is on page 42. When dealing with expressions with surds, any surd in the denominator is usually removed by rationalizing the denominator. So often what we do when we have a surd in the denominator is we remove it through this process called rationalizing the denominator. We basically do a thing where we multiply both the numerator and denominator by a term with which usually involves a surd, so that it makes the denominator a whole number. Now, often what we like to do this is to rewrite surds with a rational denominator by multiplying the numerator and denominator by the conjugate of the denominator. Now this applies for when there's binomials, but usually when there's only single terms, there's a lot easier way to actually do this, and I'll show you in a moment. Now, what does it mean for a term to be a conjugate? Well, the conjugate of a binomial expression, like the one here, so here we've got a plus b square root c. When we conjugate it, all we do is we take the negative version, so a minus b square root c. So when we're trying to rationalize the denominator, what we do is we multiply the numerator and denominator by this same conjugate. And I'll show you why we do that in a moment. But first, let's do a few examples where we just have single surd terms in the denominator. So let's have a look at the following example. So this is example 42. Rationalize the denominator in the following. So here we've got square root 7 over 2 root 3 in the first example. Now here, when we're trying to rationalize the denominator, notice there is a surd in my denominator. I don't like that surd, so what I'm going to do is I'm going to multiply both the top and bottom by that particular surd. So in these single term cases, all we need to do is just multiply both the denominator and numerator and denominator by that term. So here, it's a square root 3. I'm going to multiply both top and bottom by square root 3. What this does is it doesn't actually change the fraction. Notice here, if I multiply by square root 3 over square root 3, that's just the same as multiplying by 1. That doesn't change our number. All it does is it rewrites it in a way that the denominator is a whole number, a rational number. So here, if I multiply by square root 3 at the bottom, I get 2 square root 9, which is just, square root 9 is just 3. So this just becomes 6. You can kind of think of it as when we multiply surds, so if I do 3 times square root 3, that just cancels the square root sign and we just get 3 left over. How about at the top? Well, at the top, I would get square root 7 times square root 3. And if you remember from last lesson, when we multiply with surds, we just multiply the number inside the square root. And so here we get square root 21. And there we go. That's it for this particular question. Okay, let's have a look at the next example, B. So for B, I've got 55 over square root 11. And once again, I want to rationalize the denominator. So here, I'm going to be multiplying by, well, in this particular case, we've got a square root 11 in the denominator. So I want to multiply both the top and bottom by square root 11. And so in the denominator, I'm going to be left with 11. But in the numerator, well, the 55 isn't part of a surd, so it's just going to be 55 square root 11. Now at this point, we should also check our fraction. Can we simplify this fraction? Well, if you have a look, we can actually divide both top and bottom by a common factor. This 55 and this 11 have a common factor of 11, so I can cancel this out, and I'm left with, well, 55 divided by 11 will give me 5, and so this one here, when I cancel it out, will give me 5 square root 11. So here, when we've got single term denominators with surds, we can just multiply the top and bottom by whatever's inside that surd. Okay, so that's with this first particular case of examples. When we've got single term denominators, just like the ones we have here, we can multiply by whatever is under the surd. Now, the second example here, when we want to simplify these following expressions, hopefully you can see in this fraction, we've got a denominator which is a binomial expression. We've got 2 terms in the denominator. And so with this, we need to actually rationalize the denominator by multiplying by the conjugate. So for this example, when we want to rationalize the denominator, we don't multiply by square root 3. So let me just show you why we don't do that. So if I was to multiply by square root 3, so in the numerator I get 3 root 3, but in the denominator, well, that square root 3 would also need to multiply with that 5. And so when I multiply by square root 3, I'm going to get 5 root 3 plus 3. And that doesn't actually fix up the problem. There's still a surd in the denominator. So I don't want that in at all. So the way we actually counteract this is by multiplying. Actually, I'll leave this here just so you can see what not to do. Boop. The way we counteract this is by multiplying by the conjugate. Now, if you notice earlier, the conjugate of a plus b square root c is a minus b square root c. So for this case, what is the conjugate of the denominator? Well, in the denominator, I have a plus square root 3. And so if I want to multiply by the conjugate, that's just going to be 5 minus square root 3. And at the top, I'm also going to be multiplying by 5 minus square root 3. So let's just write this out. So in the denominator, in the numerator, I'm just going to write this as 3 brackets 5 minus square root 3 to begin with. I'm going to leave it like that for the time being. And in the denominator, I'm going to get 5 plus square root 3 times 5 minus square root 3. Now, if you have a look at the denominator, you might be going, hang on, there's still surds there. But have a look at this that we've written here, what we've written in the denominator. This is actually a particular expansion that we've looked at. If you remember, this is called a difference of two squares. I'm going to move this across so I have a bit more space. Give me a second. This is a difference of two squares. And if you remember, if I have a plus b times a minus b, that just gives me a squared minus b squared. And so when I expand out the denominator here, what I'm going to get is just 5 squared minus square root 3 squared. And when I take the square of square root 3, that just becomes a 3. And so that makes it a lot easier for me to deal with. Now, I'm still going to leave this as this bracket just for a moment, just because I want to show you, in the case something happens. So let's just deal with this. So at the bottom, I've got 5 squared, which is 25. And square root 3 squared is just going to be 3. So it's going to be 25 minus 3. And so this is going to be over 22. And there we go. Now here I would like to also check, can I simplify my fraction any further? Can I cancel out any common terms? And in this case, 3 and 22 have no common factor, so I can't cancel anything out. And I can't cancel out individual terms. And so here this just becomes, I can expand out my bracket. So I get 15 minus 3 root, minus 3 root 3 over 22. The answers seem to be wrong here. This should be a minus. So that's how we can rationalize the denominator for terms when there's binomials. When there's binomials, what we want to do is we want to multiply by the conjugate. The exact same expression, but instead of having a plus, it's a minus. If it's a minus, you change it with a plus. Okay, so that's this first example here. Let's have a look at the next example over the page. Hello, so there was a few technical issues with the video, and so I've had to re-record this particular section, so I apologize in advance. But here we are with the example over the page, example 44. So here we want to simplify this following example. 1 over 2 square root 3 minus 3 root 2. So for this example, just like we did before, we want to actually multiply by the conjugate. Now here, we've got a few terms that have coefficients or numbers at the front of the square root. We can still do the same thing. We could just going to multiply by the conjugate. So here for this particular case, if I want to multiply by the conjugate, we're just going to multiply by 2 square root 3 plus 3 square root 2. So instead of that minus, we're going to have a plus, and so we need to multiply that at the top as well. And so when we do this, the numerator, we just get 2 square root 3 plus 3 square root 2 all over, and in the denominator, 2 square root 3 minus 3 square root 2 times 2 square root 3 plus 3 square root 2. And so just like we did in the previous example, the reason why we multiply by the conjugate is so we can set up that difference of two squares. So the difference of two squares means that I square the first term. So my first term here is just 2 root 3. And when I square this, I square both the 2 on the outside and that square root 3. So when I square that 2, I'm going to get 4. And when I square that square root 3, I'm going to get 3. And so this will actually give me 12. So here for my first term, I'm going to get, so the numerator stays the same, 2 square root 3 plus 3 root 2 all over. And then the denominator, I get 2 minus, and when I do the same thing to my 3 square root 2, when I square that, I square the 3 and I get 9 times, and then when I square the 2, I get square root 2, I get a 2. So this gives me 18. So I get 12 minus 18, that will give me minus 6, and I can actually pull that minus 6 minus at the front, and so I get negative 2 square root 3 plus 3 square root 2 over 6. So once again, just like the previous example, when we are trying to rationalize the denominator, we need to multiply both the numerator and the denominator by the conjugate if it's a binomial term in the denominator. Okay, if you need to look back at any particular part, please feel free to pause the video and go back. I'm going to move on to the next and final section of this particular part of the booklet, equality of surds. Now we've got two expressions. So for example here, I've got two expressions, a plus b square root c and x plus y square root c. In order for these terms to be exactly equal, there's two conditions that have to occur. So first of all, notice there's an a and an x at the front that aren't connected to that square root c. So in order for these two expressions to be equal, I need to have a is equal to x. And hopefully you can see, well, both of them have this square root c term, which is exactly the same, but we have a b and a y in front of that square root c. And so here, in order for them to be the same, b needs to be equal to y. So if we want to check if two expressions are equal, what we do is do this process of just checking that the matching parts in each of the expressions are equal. We often call this process comparing coefficients, and in a future topic we probably will be looking at this. But here, what we want to do is we need to make sure that they match up. And so we have an example of this which requires us to actually go and rationalize the denominator. So let's have a look at this example here. Find the value of a and b if 2 over square root 5 plus 1 is equal to a plus square root b root 5. Now notice here on the left hand side, we've got this expression which has a irrational denominator. We've got a square root in the denominator. On the right hand side, we've just got a regular expression with a square root there. And so what we want to do is we want to just rationalize the denominator first, and then we'll see what we can do there. So here I've got 2 over square root 5 plus 1. So when I rationalize the denominator, I'm going to multiply by the conjugate, 5 minus 1, square root 5 minus 1, for both the numerator and the denominator. So in my numerator, I'm going to get 2 brackets square root 5 minus 1. I'm going to leave it as that for now. Over, and in the denominator, I'm going to get the difference of two squares. Now, once you start to do this question a few more times, hopefully you'll start to actually get the pattern, and you can actually do this next step without having to do very many, write all the working out. So with the difference of two squares, we square the first term, so root 5 squared. When I square root a root, I just get the number that's left in it, so it's going to be 5. And the second term, 1 squared is just 1, so it's going to be 5 minus 1. And so here we get 2 square root 5 minus 1 over 4. Now there's a reason why I left the numerator in factorized form with that bracket, and that's because we can actually cancel out occasionally. So here, if you have a look, I've got a 2 and a 4, and so what I'm going to do is I'm actually going to cancel out the common factor here. So both of these actually have a common factor of 2, so I'm left with 1 at the top and 2 at the bottom, and so I get square root 5 minus 1 over 2. And so we've rationalized the denominator. But you might be looking at this and going, hang on, this doesn't quite look like my expression a plus b square root 5 yet. What can I do here? Well, what we can actually do is we can just rearrange this square root 5 minus 1 over 2 to make it look a little bit like my expression here. So how do I do that? Well, the first thing I'm going to do is I'm actually going to rewrite the order. So here I have negative square root 5 minus 1. I'm going to just rewrite this as negative 1 plus square root 5 over 2. That's actually the same thing. All I've done is just swap the order of my terms. Here, this would be like the same as doing 3 minus 2 and then changing that to be negative 2 plus 3. This gives you the same thing, answer of 1 and 1. All I've done is just rewritten the order. Now the next thing I'm going to do is I'm going to split the fraction. Now you can do that. You can just rewrite this as negative 1/2 plus square root 5 over 2. So I've just split the fraction into two parts based off the two terms in my numerator. So here I've just split the fraction in two, and hopefully you're starting to see, hang on, this is starting to look a little bit like my expression here, a plus b over 5. Just one final thing to do. If you've got a denominator of 2, that's just the same as halving something. So I can rewrite this as actually a negative half plus a half times square root 5. And hopefully here you can actually start to see how this looks exactly like my expression here. All we need to do is just compare coefficients. So a, if you have a look in the first expression, matches up with this minus a half in the second one. So I can write here, therefore a is going to be equal to negative a half. And we have b over here, which is the coefficient of that 5, or the number in front of the 5, square root 5, and that happens to be this half over here. So I'm going to write here, b is equal to a half. And there we go. That's how we can compare coefficients and get equality between surds. So just a brief summary of what we did in this lesson. In this lesson, we looked at rationalizing the denominator. What happens when you have an irrational denominator, a denominator where there is a square root in the denominator, and how do we actually go about rewriting the fraction so that there's no square root in the bottom. And so what we need to do is either if it's a single term, we just multiply the top and bottom by the surd in the denominator, or if it's a binomial expression like we did here, we need to multiply by the conjugate and use the difference of two squares to make the bottom a whole number. So hopefully that helped, and if you have any further questions, feel free to message me or send me an email. I'm more than happy to answer, and there should be a few questions for you to have a go at on your own from the textbook. So until then, Year 11s, I'll see you guys next lesson. Bye!